Okay, well, in this video we're going to look again at the helical antenna, and the idea of this video is to demonstrate how interesting and didactically useful it is to be able to visualize fields and to see what is happening at the ports of the coaxial cables, transmission lines are connected to the structure or antenna in this case. Now, here we have the helical antenna consists of three parts: the copper helical structure, then we have a dielectric. If I just look at this, we can see it, the dielectric part, the helical, which is also forms the inner of the coax, and the ground plane, which is aluminium in this case. Although the fact that there's different metals doesn't really make much difference for antennas. If it were resonators, it certainly would make a difference, but in this case it doesn't. Now I've changed this so we're looking at an impulse or a pulse wave simulation. Just before I do that, let's just look at how it was sampled. Here we see the day meter areas and intersections with the structure itself, and we can confirm that none of those are there's a small one here, and there's another small one. So this, when I have colors here, I indicate that there's certain parts of the structure that are inevitably going to have a small sampling. That means our time step was small. We can actually check graphically how the day distance and the lengths are related for certain directions, X, Y, and Z, and we can improve. The students will be working a little bit on that, trying to improve the meshing of the geometry. So that's one of the things we control in Blender itself, because we have a definition of the mesh, especially at sensitive points on the structure. So let's launch the simulation. Well, we can actually see also what it's going to look like from a sample point of view, the structure itself. Now let's launch the simulation. It's going to launch itself on, there it goes. This is all in real time. If I just stop here and explain, we're seeing the field, the electric field, the axial component in green, and the red and blue components are the transverse components. For a particular level, which is controlled here by this number, if I decrease that number, you can see that the field we're viewing, well, it appears to get bigger. That's because that lower level field has it's traveled further out in that particular time, and it exists here. If we let that continue, and we'll see, and I can increase this level again, so we can see a particular level of field that looks as if it's bound to the structure. This is the level of field I'm interested in this particular moment. Here I'm saying, I'll just stop the simulation. Here I'm saying the incident pulse being fed to the feed point in here in red, and the reflected voltage wave that's seen at that feed point in blue. And as time goes on, this, well, it would be charged, I suppose. It's been traveling down the structure. Eventually it runs out of structure, ends up bouncing off the end. So you see what looks like a wave of field traveling back, and you notice it's rotating in the opposite sense as it travels backwards. And at around about 9 nanoseconds, it enters back into the coaxial cable, just about 8 or 9. So when this is updated again, we'll see. And then of course a lot of it is absorbed by the 50 ohm port impedance here, but some of it gets reflected back and travels back down the structure again. Here we saw that. That's a reflection to about 8 or 9. Now we should see another reflection, which happens at a time corresponding to the time it takes it to travel here, here, and back again. And that's going to happen at about 18 nanoseconds. And here we're seeing the S parameter in the frequency domain obviously that's just the Fourier transform of the blue one divided by the Fourier transform of the red one. This is what I was saying, at about 18 nanoseconds we're seeing a second group of reflected pulses, and it's spreading out more and more each time. So basically the students will understand, because they'll see that there's a wave traveling down the structure. That's why it's called a traveling wave antenna. The structure is finite, so some of it gets reflected. They won't see the radiation part because I have to visualize a weaker field level. The strong field is actually bound to the structure. It looks like that it's happening. But they will see this interaction happening between the end of the structure and this feed. So what we're going to get them to do is adjust the dielectric constant, adjust this length until we get a better match, so that the only thing that's going to exist basically is this part, and that should disappear. Then if we have more time, we can do something to the end here. We can investigate, because this is drawn in Blender, that you can do wonderful things and make this go to a smooth point, or change, look at the typical thing people do to make this reflection here somewhat less. Now if you look at this in the frequency domain, not the frequency domain, if you look at as a frequency simulation with a single frequency, I'm confusing people because I'm actually using a time domain simulator, but I'm going to put a single sinusoidal excitation, and we'll look at what happens starting off again. This time the fields should be stronger because it's a sinusoidal signal. And here we're saying, let's give my little algorithm some problems here, but now we're saying the green field that's indicating the axial field components are primarily stuck to this end here. As you'd expect, it only exists the normal field. The tangential field on the ground plane has to be 0, so there shouldn't be any, and there isn't red or blue on this end. Towards this end here, we're saying a rotation. Because this is circular polarization, we should see the field rotating basically as time progresses. The field is rotating, the polarization of the field is rotating, and it should be giving us an almost perfect circular polarization. Obviously when it's reflected from the end, that's going to disturb that somewhat. If I reduce the field level that I'm looking at, I can see better the fields that are actually propagated. In this particular simulation, my FDT space is more, actually it's quite small. As we can see, it's that size. It's relatively small. I can make this bigger, and if I make it bigger, I will be able to see the waves that are actually the waves are able to escape off the end of the structure. So I will see blobs of field launching themselves, propagating in this direction. Here it's a bit difficult to see because we're visualizing, we don't have enough space, FDT space, and we're visualizing fields that are just too strong. Those fields are really the fields that are existing bound to the structure itself. Sometimes called reactive fields, aren't they? Evanescent fields. Those are the fields that exist to maintain the boundary conditions around the structure. You can see the magnetic field and the electric field do the same thing. And that indicates that it's going to be a circular polarization. Basically, that's what our students are going to be doing, to look at design aspects of this from a visualization point of view, and to understand the operation of the antenna. Obviously, to understand why the helical structure gives us a rail impedance, and what that impedance is a different matter, but we shall see how they take this when time comes. I hope you enjoyed the video.